Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Main electricity. Mains electricity is the electricity generated by power stations and transported around the country through the national grid. Main electricity is an alternating current supply. An alternating current is the current flow back and forth. In the UK, the domestic electricity supply has a frequency of 50 Hz and a voltage of about 230 volts. A frequency of 50 Hz means the direction of the current changes back and forth 50 times every second. Main circuits. Main circuits usually consist of 3 wires: the live wire, the neutral wire and the earth wire. The live wire provides the path along which the electrical energy from the power station travels. This wire is brown insulated and carries the alternating voltage of negative 230 volts and positive 230 volts, making the current flow backwards and forwards through the circuit. The neutral wire completes the circuit, and it is kept at 0 volt. This wire is blue insulated. The earth wire usually has no current in it. It is there to protect you if an appliance develops a fault. It provides a path for current to escape without passing through the user. This wire is yellow-green insulated. Ring main circuits provide a way of allowing several appliances in different parts of the same room to be connected to the mains using the minimum amount of wiring. In a figure is shown the ring main circuit in a room. This is a socket set in wall. These wires are connected to a consumer unit. Plug and sockets. Plugs and sockets in different countries look different, but the principles rules of electrical wiring are similar. In the UK, 3-pin plugs are used to connect appliances to the mains circuit. The 3 pins are for the live wire, the neutral wire, and the earth wire. This pin is connected to the neutral wire. The middle pin is connected to the earth wire. This pin is connected to the live wire and then connected to the fuse. When wiring a plug, check the following. Wires are connected to the correct terminals, using the color code on the left. The cable is held firmly by the grip. The correct fuse is fitted. The 3-pin plug is connected to the appliance and then plug in the socket when it is used. In a figure, a kettle is plugged into a mains socket. It is connecting to a main circuit. Then the electrical energy comes from a generator in a power station to the kettle. In a figure, you see that the earth wire to connect with the metal casing of the appliance. A fuse is placed at the live wire. A switch is placed at the live wire. Fuse is connected in the live wire for safety. Fuse is a thin piece of wire. This is a symbol of fuse. If too much current flows through the circuit, the fuse will get overheats and melts to blow and break the circuit. This prevents the user getting a shock, the cable overheating and catching fire, and saving devices in electrical appliances. Once the fault causing the increase in current has been corrected, the blown fuse must be replaced with a new one of the same size before the appliance can be used again. Circuit breaker is used in your consumer unit, are often in the form of trip switches. If too large a current flows in a circuit, a switch automatically opens, making the circuit incomplete. Once the fault in the circuit has been corrected, the switch is reset, usually by pressing a reset button. There is no need for the switch or circuit breaker to be replaced, as there is when fuses are used. Switch is connected in the live wire for safety. With the switch open and connected into the live wire, the current cannot reach the appliance. The user is safe from electric shock. With the switch open and connected into the neutral wire, the current can reach the faulty appliance. The user is not safe from electric shock. Earth wire. Earth wire is a safety wire that connects the metal body of an appliance to earth. This prevents the appliance from becoming live. If the live wire comes loose and touches the metal body, a current immediately flows to earth and blows the fuse. This means that the appliance is then safe to touch. If the appliance has no earth wire and the live wire comes loose, a current could flow through the user, causing an electric shock. Double insulated appliances. Some appliances do not have an earth wire. This is because their outer case is made of plastic rather than metal. The plastic acts as an extra layer of insulation around the wires, which prevents any current from flowing to the user even if the live wire comes loose inside the appliance. Heating effect of current. Heating effect of current in wires or appliances causes by their resistance and current passing through them. The wiring in a house is designed to let current pass through it easily. As a result, the wires do not become warm when appliances are being used. We say that the wires have a low resistance and lower heating effect. These wires are made of a copper with insulating. A light bulb. When current passes through the very thin wire filament of a traditional light bulb, it becomes very hot and glows white. The bulb is transferring electrical energy to heat and light energy. Other common appliances that make use of the heating effect of electricity include kettles, electric ovens, toasters, electric fires and hairdryers. They want wires, more usually called heating elements, to become warm. The wires of a heating element are designed to have a high resistance, so that as the current passes through them, energy is transferred and the element heats up. Electrical power. Electrical power is the transferred energy per unit time. We can written the equation as P equals E over T, where P is the power in watt, E is transferred energy in joule, T is the time in second. A 70 watts light bulb transfers 70 joules of electrical energy every second to heat and light. A 50 watt light bulb transfers 50 joules of electrical energy every second to heat and light. The 70 watts bulb will be brighter because it transfers higher electrical energy every second. The power of an appliance is related to the voltage across it and the current flowing through it. We can written the equation as P equals VI, where P is the power in watt, V is the voltage in volt, I is the current in ampere. Electrical energy. Rearranging the energy transfer and power equation, the energy can be written as E equals PT. We substitute P equals VI. So, we can be written the formula for the electrical energy as E equals VIT. The amount of energy an appliance transfers depends on how long the appliance is switched on. The power of the appliance. Fuse values. The plug is usually fitted with either a 3 amperes, 5 amperes, or 13 amperes fuse. The value tells you the current needed to blow the fuse. It must be greater than the normal current through the appliance, but as close to it as possible, so that the fuse will blow as soon as the current gets too high. If you know the power of an appliance, you can use the equation of P equals VI to work out whether a 3 amperes, 5 amperes, or 13 amperes fuse is needed. For example, calculate the correct fuse that should be used for 2300 watts, 230 volts, kettle. Current equals power over voltage equals 2300 over 230 is equal to 10 amperes. So, a 13 amperes fuse is needed. TV, 550 watts, 230 volts. Current equals power over voltage equals 550 over 230 is equal to 2.4 amperes. So, a 3 amperes fuse is needed. The TV would still work with a 13 amperes fuse. But if a fault developed, its circuits might overheat and catch fire without the fuse blowing. Alternating current is the current to flow forward and backward. This current draws from mains electricity of house and generator. Its value increases and then decreases and then does the same again, but in the opposite direction. If we could draw these changes as a graph, they would look like a wave. Direct current is the current to flow in one direction. This current draws from a dry cell or battery. Cells and batteries provide currents and voltages that are always in the same direction and have the same value. This is called direct current or direct voltage. If we drew this as a graph, it would be a straight horizontal line. Electrical hazards from main electricity. Mains electricity is potentially lethal because it can carry high voltages and currents. Even voltages as low as 50 volts can pose a serious hazard to individuals, especially if the current is high enough. Common hazards include damaged insulation. If someone touches an exposed piece of wire, they could be subjected to a lethal shock. Overheating of cables. Passing too much current through too small a wire, or leaving a long length of wire tightly coiled, can lead to the wire overheating. This could cause a fire or melt the insulations, exposing live wires. Damp conditions. If moisture comes into contact with live wires, the moisture could conduct electricity, either causing a short circuit within a device, which could cause a fire, or posing an electrocution risk. Excess current from overloading of plugs, extension leads, single and multiple sockets when using a mains supply. If plugs or sockets become overloaded due to plugging in too many components, the heat created can cause fires. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Electric current. The electric current is related to the flow of charge. So the definition of electric current is the amount of charges passing a point per second. We can rewrote the equation as I equals Q over T, where I is the current in ampere, Q is the amount of charge in coulomb, T is the time in second. So, 1 ampere is 1 coulomb per second. The direction of current is same to the direction of moving of positive charges, while the direction of current is opposite to the direction of moving of the negative charges. Conductors. Conductor is material that allows charge, usually electrons, to flow through it easily. This is because it has free-moving electrons. Electrons flow easily through all metals. We therefore describe metals as being good conductors of electricity. In metals, some electrons are free to move between the atoms. Under normal circumstances, this movement is random. That is, the number of electrons flowing in any one direction is roughly equal to the number flowing in the opposite direction. There is therefore no overall flow of charge, and no electric current. If, however, a cell or battery is connected across the conductor, more of the electrons now flow in the direction away from the negative terminal and towards the positive terminal. We say there is now a net flow of charge. This flow of charge is what we call an electric current, that its direction from positive to negative terminal. The greater the flow of charge, the greater the electric current. Insulators. Insulators is a material that does not allow the flow of charge through them very easily. This is because it has no free-moving electrons. Electrons do not flow easily through plastics, rubbers, glasses or woods, so they are poor conductors of electricity. In insulators, all the electrons are held tightly in position nucleus and are unable to move from atom to atom. Charges are therefore unable to move through insulator. Measuring current. A simple circuit is shown on the diagram. This is a cell. This is a light bulb. This is an ammeter. It is used to measure the current in a circuit. It must connect in series. Good ammeter should has low resistance to allow more charges to flow through it. This is the connecting wire, which is made of copper, because a copper is a good conductor. We can draw the diagram of this circuit in the symbol of each component as shown. This symbol is a cell. Longest side is indicated a positive. Shortest side is indicated a negative. The convectional free-moving electrons in a copper flow from a negative terminal to a positive terminal of a cell, while the convectional current flow from a positive terminal to a negative terminal of a cell. This symbol is a light bulb. This symbol is an ammeter. Voltage. Voltage is the transfer energy per unit charge that passing charge through a component or a circuit. We can written the equation as V equals E over Q, where V is voltage in volts, E is energy in joules, Q is charge in coulombs. So, 1 volt equals 1 joule per coulomb. We often use cells or batteries to move charges around circuits. We can imagine them as being electron pumps. They transfer energy to the charges. The amount of energy given to the charges by a cell or battery is measured in volts. If we connect a 9-volt cell into a circuit, and current flows, 9 joules of energy is given to each coulomb of charge that passes through the cell. As the charges flow around a circuit, the energy they carry is transferred by the components they pass through. For example, when current passes through a bulb, energy is transferred to the surroundings as heat and light. Measuring voltage. We measure voltages using a voltmeter. This is the symbol of a voltmeter. The voltmeters are connected across, or in the parallel with, the cell and a light bulb. Good voltmeter should has very high resistance to block the current to flow through it. A voltmeter connected across a cell, or battery, will measure the energy given to each coulomb of charge that passes through it. A voltmeter connected across a component will measure the electrical energy transferred when each coulomb of charge passes through it. Series circuits. A series circuit is a simple loop circuit with no branches or junctions. There is only one path for the current to follow. In a series circuit containing 3 identical bulbs as shown, a single switch placed anywhere in the circuit can turn all the bulbs on and off. If a switch S2 opens, the other bulbs will stop working, and if it closes, the other bulbs start working. If a switch S1 opens, the other bulbs will stop working, and if it closes, the other bulbs start working. If any one of the bulbs breaks, it creates a gap in the circuit, and all of the other bulbs will stop working. We can conclude that the current has the same value in all parts of the circuit. Current is not used up. The size of the current in a series circuit depends on the voltage supplied to it and the number and type of the other components in the circuit. If a second identical cell is added in series, the voltage will double, and so the current will also double, causing bulbs are brighter. The energy supplied by the cell is shared between all the bulbs. This means that the voltage from cell is shared across each bulb. In a series circuit, sum of voltage across each bulb is equal to voltage across a cell. So the more bulbs you add to a series circuit, the less bright they all become. Decorative lights are often wired in series. Each bulb only needs a low voltage, so even when the voltage from the mains supply is shared out between them, each bulb still gets enough energy to produce light. Unfortunately, if the filament in one of the bulbs breaks, then all the other bulbs will go out. Parallel circuits. A parallel circuit is a circuit with branches or junctions, providing more than one path for the current to follow. In a parallel circuit containing 3 identical bulbs as shown, Switches can be placed in different parts of the circuit to switch each bulb on and off individually, or all together. If a switch S3 opens, only the bulb on the same branch to turn off. If a switch S1 opens, all bulbs to turn off. If one bulb breaks, only the bulbs on the same branch are affected. This means the current from the cell is shared in each the branch. So the number of electrons that flow into a junction each second must be equal to the number that leave each second. This means that the currents entering a junction must always be equal to those that leave. At the junction P in the circuit, the current that enters junctions is 0.6 amperes and the current that leaves is 0.4 amperes plus 0.2 amperes equals 0.6 amperes. Each branch of the circuit receives the same voltage, so if more bulbs are added to a circuit in parallel, they all keep the same brightness. This means that the voltage remains the same across each branch and is equal to the voltage across the cell or battery. The lights in your home are wired in parallel. This is why you can switch lights on and off separately, and the brightness remains unaffected when other lights are turned on or off. Also, if a bulb breaks or is removed, you can still use the other lights. Resistance. We measure the resistance, R, of a component by comparing the size of the current, I, in that component and the voltage, V, applied across its ends. Voltage, current and resistance are related as follows. Voltage, V, in volts equals resistance, R, in ohms times current, I, in amperes. We measure resistance in units called ohms. 1 ohm is 1 volt per ampere. A battery transfers the energy to the charges for driving the charges to move around the circuit. All components in a circuit offer some resistance to the flow of charge. For example, connecting wires allow charges to pass through very easily, losing very little of their energy. The flow of charge through some components is not so easy, and a large amount of energy may be used to move the charges through them. This energy is transferred, usually as heat and other form of energy. For example, a fixed resistor, the electrical energy is transferred to heat when the charge passing through it. This symbol is a fixed resistor. A light bulb, the electrical energy is transferred to heat and light when the charge passing through it. If the circuit has no the resistor, the current is too high and the bulb breaks. The variable resistors, as it is possible to alter their resistance. This is the variable resistors and their symbol. If you alter the volume of your radio using a knob, you are using a variable resistor to do this. In the circuit in figure, a variable resistor is being used to control the size of the current in a bulb. If the resistance is increased, the current will be smaller, and the bulb will glow less brightly, or not at all. If the resistance is decreased, there will be a larger current, and the bulb shines more brightly. The variable resistor is behaving in this circuit as a dimmer switch. In the circuit contains a 12V battery, and 2 resistors connected in series. Calculate the current in each of the resistors. Their total resistance is found by simply adding the individual resistances together. This is not true for parallel circuits. You do not need to know how to do this. So, the total resistance the current must pass through is 2 ohms plus 4 ohms equals 6 ohms. Voltage across both resistors is 12 volts. So, the current in the circuit is V divided by total resistance, R, which is 12 volts divided by 6 ohms, it is equal to 2 amperes. The current in a series circuit is the same everywhere. So the current in both resistors is 2 amperes. Calculate the voltage across each resistor. The voltage across 2 ohms resistor is V equals I, R, equals 2 amperes times 2 ohms, it is equal to 4 volts. The voltage across 4 ohms resistor is V equals I, R, equals 2 amperes times 4 ohms, it is equal to 8 volts. Experiment to investigate how current varies with voltage for different wires. Set up the circuit shown in figure. Turn the variable resistor to its maximum value. Close the switch and take the readings from the ammeter and the voltmeter. Alter the value of the variable resistor again, and take a new pair of readings from the meters. Repeat the whole process at least 6 times. Place the results in a table and draw a graph of current against voltage. The graph is a straight line graph passing through the origin. The slope is constant, so the resistance of this wire does not change. The resistance of a wire is 1 over the slope. The steeper the slope, the smaller the resistance of the wire. If we repeat this experiments for other components, such as a resistor, a filament bulb and a diode, the shapes of the graphs we obtain are often very different to that shown in the next. We repeat the experiment to investigate how current varies with voltage for resistor. Set up the circuit shown in figure. Alter the value of the variable resistor, and take the readings from the meters. Repeat the whole process at least 6 times. Reverse a cell and repeat the all steps as the previous. Place the results in a table. And draw a graph of current against voltage. The graph is a straight line passing through the origin. It has a constant slope, so the resistance of this resistor does not change. Therefore, the resistance of a resistor is 1 over the slope. The steeper the slope, the smaller the resistance of the wire. This side of the graph comes from the result that we reverse the battery. We repeat the experiment to investigate how current varies with voltage for a light bulb. Set up the circuit shown in figure. Alter the value of the variable resistor, and take the readings from the meters. Repeat the whole process at least 6 times. Reverse a cell and repeat the all steps as the previous. Place the results in a table and draw a graph of current against voltage. The graph is not a straight line. This shows that resistance of the bulb changes. The slope of the graph decreases. This shows that the rate of increasing voltage is greater than the rate of increasing current. This means that the resistance of filament to increase. This is because at higher current and voltage to create the more heating effect, causing the resistance of filament to increase. This side of the graph comes from the results that we reverse the battery. We repeat the experiment to investigate how current varies with voltage for a diode. Set up the circuit shown in figure. Alter the value of the variable resistor, and take the readings from the meters. Repeat the whole process at least 6 times. Reverse a cell and repeat the all steps as the previous. Place the results in a table and draw a graph of current against voltage. This strangely shaped graph shows that diodes have a high resistance when the current is in one direction, and a low resistance when it is in the opposite direction. This side of the graph shows that a diode has low resistance, causing the current to flow. This side of the graph comes from the results that we reverse the battery. The resistance of a diode has very high resistance, causing no current to flow. Diode is a component that allows current to flow in one direction. This is the symbol of a diode. Current is allowed to flow in this direction. For the first circuit diagram, the current flows from the positive to negative terminal. So the diode allows the current to pass through, causing a bulb turns on and shining bright. For the second circuit diagram, the battery is reversed. This causes the current from the positive terminal to be blocked by the diode, causing a bulb turns off. Diodes are used in rectifier circuits that convert alternating current into direct current. A light-emitting diode, or LED, glows when current flows through it in the correct direction. This is the symbol of a light-emitting diode. It glows when current flows in this direction. For the first circuit diagram, the current flows from the positive to negative terminal. The light-emitting diode allows current to pass through, causing it to glow brightly. For the second circuit diagram, the battery is reversed. This causes the current from the positive terminal to be blocked by the light-emitting diode, causing it to not glow. A thermistor is a temperature sensor. This symbol is a thermistor. A thermistor decreases its resistance when the temperature increases, and it increases its resistance when the temperature decreases. The graph shows thermistors decreasing resistance with increasing temperature. In the circuit diagram, when temperature increases, the thermistor's resistance decreases, causing the current from the battery to increase. This causes a light bulb to shine brighter. Thermistors are used in temperature-sensitive circuits in devices such as fire alarms. They are also used in devices where it is important to make sure there is no change in temperature, for example, in freezers and computers. A light-dependent resistor, or LDR, is a light intensity sensor. This symbol is a light-dependent resistor. A light-dependent resistor, LDR, has a resistance that changes when light is shone on it. In the dark, its resistance is high, while, when light is shone on it, its resistance decreases. The graph shows LDR's decreasing resistance with increasing light intensity. In the circuit diagram, when the light shine on the LDR's resistance decreases, causing the current from the battery to increase. This causes a light bulb to shine brighter. Light-dependent resistors are often used in light-sensitive circuits in devices such as photographic exposure equipment, automatic lighting controls, and burglar alarms. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Electric charge. Objects can be given one of two types of electric charge, positive and negative. When two charged objects are brought close together, there will be a force between those objects. Like charges repel. Unlike charges attract. Electric charge is measured in units called coulombs. Where charges come from? Everything is made of tiny called atoms. They have electric charges inside them. A simple model of the atom is shown on the diagram. There is a central nucleus made up of protons and neutrons. Protons have a positive charge. Neutrons have no charge. Much lighter electrons are orbiting around a nucleus. Electrons have a negative charge. Atoms have equal numbers of electrons and protons, so the net charge is zero. This is called the neutral atom. When the atoms lost the electrons, so the number of electrons less than the number of protons, and the net charge is a positive. This is called a positive ion atom. When the atoms gain the electrons, so the number of electrons more than the number of protons, and the net charge is a negative. This is called a negative ion atom. Conductors and insulators. A conductor is a material that allows charge, usually electrons, to flow through it easily. This is because it has free-moving electrons. Conductors tend to be metals. For example of the material that order from best conductor to the poorest conductor, as shown on the diagram. Metals conduct electricity very well, because current is the rate of flow of charged particles. An insulator is a material that does not allow the flow of charge through them very easily. This is because it has no free-moving electrons. For example of insulators are rubber, plastic, glass, and wood. Some nonmetals, such as graphite, allow some charge to pass through them, so the graphite is conductor. Investigate how an insulator can be charged by friction. When the uncharged plastic rod is rubbed with an uncharged cloth, the friction causes the electrons transfer from the rod to the cloth. This causes the cloth to become a negative charge, and the plastic rod to become a positive charge. Electrostatic phenomena. Rub the plastic ruler on the cloth or sleeve of your jumper. The ruler will become charged. We have assumed that the ruler has become positively charged. If it is held close to some small, uncharged pieces of paper, some electrons within the paper will be attracted to the edges closest to the ruler. There will be an attraction between these negative parts of the paper and the positive ruler. A comb attracts your hair when you are brushing, because the friction causes negative charges to transfer between the comb and your hair. The comb and hair become oppositely charged, which is why they are attracted together. A negatively charged balloon attracts the positive charges in the stream of water. The stream of water bends toward the balloon, because the attractive force between unlike charges is greater than the repulsive force between like charges. A negatively charged balloon strikes a wall, because it repels the negative charges in the atoms on the wall. This causes the negative charges on the wall to move away the balloon. The attractive force between unlike charges is greater than the repulsive force between like charges, which is why the balloon sticks to the wall. Lightning during the thunderstorm. The attractive force between the bottom of the clouds and the positive charges at the ground causes negative charges to travel from the cloud to the ground. This creates an electric current. The electrical energy is transferred to light, heat, and sound energies. Uses of static electricity. Electrostatic paint spraying. Painting an awkwardly shaped object, such as a bicycle frame, with a spray gun can take a long time and use a lot of paint. Using electrostatic spraying can make the process much more efficient. As the drops of paint emerge from the spray gun, they are charged. As the drops all carry the same charge, they repel and spread out, forming a thin spray. The metal bicycle frame has a wire attached to an electrical supply, giving the frame the opposite charge. The paint drops are therefore attracted to the surface of the frame. There is the added benefit that paint is attracted into places, such as corners and behind the frame, that would normally be hard to reach. Inkjet printers. Modern inkjet printers use a technology called inkjet to precisely place tiny drops of ink onto paper. They achieve this by using electrostatic forces. Each ink droplet receives a charge. This is the negatively charged ink drops. As it travels between a pair of deflection plates, these electrostatic forces guide it to the exact position on the paper. This is the alternating the charges on the deflection plates charges the position of the ink dot on the paper. This is printed paper. The charges on the plates change hundreds of times each second, so that each drop falls in a different position, forming pictures and words on the paper as required, as shown on the diagram. This is how the final image is created. Photocopiers. Positive charges are applied to a rotating drum coated with selenium, a light-sensitive metal. A bright light shines on the document to be copied. The white areas reflect light onto the drum, while the dark areas, text and images, absorb the light. Where the light strikes the drum, the positive charge is lost. Negatively charged toner, a fine black powder, is attracted to the remaining positive areas on the drum, creating an image of the document. Surplus toner is removed at here. A sheet of paper with a positive charge is then pressed against the drum, picking up the toner particles. Finally, heat melts the toner, permanently fusing it to the paper, creating the copy. Problems with static electricity. Friction with air causes aircraft to accumulate static electricity during flight. Upon landing, this built-up charge can discharge as a spark, posing a serious risk of explosion if it occurs during refueling. To prevent this hazard, aircraft are grounded with a conductor as soon as they land and before refueling begins, allowing the static electricity to safely dissipate. Similarly, fuel tankers transporting fuel on roads must also be grounded before transferring any fuel to prevent sparks that could ignite a fire or explosion. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.